Imagine you're an aviation engineer in the 1940s, and someone pitches you a design for a new helicopter. But instead of a standard rotor, it has one solitary blade. To keep the whole thing from tearing itself apart in midair, there is a massive counterweight bolted to the other side of the hub. Then the pitch gets weirder. The engineer explains that once you're done hovering, you're going to stop that single blade completely mid-flight, fold it up, pull it down inside the aircraft, and fly away on delta wings like a jet. The Sikorsky XV-2 was an actual, fully funded military program from the 1950s. Building a one-bladed transforming jet sounds absurd, but the engineers at Sikorsky weren't crazy. They were trying to solve a very real, very stubborn problem in aerodynamics. Helicopters have a strict speed limit. You can put the most powerful engine in the world inside a chopper, but physics enforces a hard barrier right around 200 miles per hour. This animation shows exactly why that limit exists. It's an aerodynamic quirk called retreating blade stall. As the helicopter flies forward, the blade advancing into the wind adds the speed of the aircraft to its own rotational speed, generating high lift. But on the other side, the retreating blade is moving away from the wind. The forward speed of the helicopter subtracts from the air flowing over that blade, leaving it with barely enough airflow to generate any lift at all. Push the aircraft too fast, and that asymmetry becomes a serious problem. The side with lift pushes up, the side without lift drops, and the whole helicopter will violently and aggressively tilt until it flips itself completely over. By 1950, the US military had a major dilemma. They needed aircraft that could hover perfectly still for reconnaissance and rescue missions, but they also needed them to cruise at 400 miles per hour to keep up with the new generation of jet fighters. To get vertical takeoff capabilities and high-speed jet flight in the same machine, engineers realized they had to figure out a way to completely erase the helicopter rotor mid-flight. Igor Sikorsky's team came to the table with an elegant theory. If the rotor is holding the aircraft back, just stop it, fold it up, hide it entirely inside the fuselage, and seamlessly transition to flying on wings alone. The immediate problem with stowed rotors is simple geometry. Helicopter rotors are massive, and the inside of a sleek aerodynamic jet fuselage is incredibly tight. This blueprint illustrates Sikorsky's radical workaround. A standard four-blade rotor physically cannot fold down enough to fit, so the engineers sliced the whole assembly down to a single blade. By adding a compact, heavy counterweight to balance the spin, they reduced the storage footprint by half. That design choice created another major hurdle. Spinning a blade requires a heavy gearbox. That gearbox generates a massive twisting force, or torque, that wants to spin the entire body of the aircraft in the opposite direction. This is exactly why standard helicopters need a tail rotor to stay straight. Since a tail rotor would ruin the jet's aerodynamics, Sikorsky eliminated the gearbox entirely. Instead, they took compressed air from a rear jet engine, routed it up through a hollow center mast, down the inside of the blade, and blasted it out of a nozzle right at the tip. It spun the blade like a pinwheel, generating lift with absolutely zero torque on the fuselage. In their pursuit of an aerodynamically flawless jet profile, Sikorsky's engineers had backed themselves into designing a mechanical anomaly, a tip jet-driven, single-bladed rotor that no one had ever successfully built. To see if any of this would actually work, they ran a real-world test in August of 1948. The team strapped a single-bladed rotor and its counterweight onto an old R-4 helicopter and powered it up. The blade spun and it successfully generated lift, but there was a severe physical penalty. A standard rotor distributes its lift across multiple blades, but one blade delivers a single violent pulse of upward force on every single revolution. The test aircraft shook so aggressively it threatened to tear itself apart. Those horrendous vibrations forced a cycle of compromises. Sikorsky had to evolve the design from one blade to two, and eventually to four, to smooth out the ride. But every time they added a blade, the folding and retracting mechanisms required to stow them grew heavier and infinitely more complicated. Despite years of wind tunnel tests mapping out these new folding mechanisms, the XV-2 program hit an insurmountable roadblock in 1958. The launch of Sputnik triggered the space race, and overnight, defense budgets pivoted away from experimental aircraft and poured directly into satellites and missiles. American forces desperately needed a rescue aircraft fast enough to reach downed pilots deep in the jungle before enemy forces arrived, but capable of slowing down to a dead hover for the extraction. Sikorsky brought their stowed rotor back to the drawing board, but they were up against a competitor from that original 1950s competition, the Bell XV-3. Bell approached the physics problem from a totally different angle. Instead of elegantly trying to fold the rotors and hide everything away, their design used sheer brute force. They mounted massive propellers on the ends of the wings and simply tilted the entire assemblies forward for forward flight. The XV-3 was heavy, mechanically unforgiving, and early prototypes nearly killed their test pilots. But the core concept worked. That brute force approach survived decades of iteration, ultimately resulting in the V-22 Osprey. The Sikorsky XV-2 remains a masterpiece of theoretical design, a machine that promised zero aerodynamic compromises in either mode. But in the hangar, elegance is a liability. The one-bladed jet was simply too clever for its own good, ultimately proving that successful engineering isn't about the beauty of the concept, but the reliability of the build.